Good day, everyone. My name is Steven Haeg, and today I'm going to be presenting a portion of the test rig design class. So this is part of a two-day class. We're going to talk for about a half an hour today with a couple of the key points. You may wonder who I am. My name is Steven Haeg. I've been working at MTS now for over 40 years, been in engineering in ground vehicles and such like for about 42 years total. Basically, my job is to work with customers, MTS customers, and technologies to see what we can do to help. In the process, I've designed and worked on some of 2,000 test rigs, and so I can share some of that information that we've gained over this class. Test rig development process, as you can see, is a comprehensive and complete one. It starts with definition, design, fabrication, integration, and into development. The class will talk about the first three steps there: test concept definition, test rig criteria, and component selection. After that, you get into fabrication and assembly, of course. That's not something we'll be teaching in the class itself. The objective here is to get to a logical breakpoint. People want to get a requirement for a test and walk back to the warehouse and start pulling brackets and actuators and stuff together. What are you going to do? How are you going to do it? How are you going to lay it out? How is it going to work well to get you good data? Let's sit down first and let's make some sketches and get some specifications written. That's what the test concept definition section is about. And today we'll talk a little bit about that specific part of the design criteria. So what we're going to come out with is a statement of needs, some words and drawings that says this is what we're going to do and how we're going to do it. There's a lot of different ways we can develop our products. Of course, real use is the real thing. It can't really be argued with, but neither can it easily be measured or repeated. So it's difficult for us to do development stuff on that field. It's also very late in the development cycle when we've got running prototypes that are comprehensive and complete. So they make a proving ground, a subset of the entire world, and every company's got slightly different criteria for their proving ground, for a little different product mix. But that tends to be what they call their reference, the ground zero for doing their testing. Now, of course, you're subject to vagaries of weather, of people, of all kinds of other things when you're driving cars around the proving ground. The repeatability is 2 or 4 times worse than it is in the laboratory. It's difficult to make engineering decisions. So in today's modern lab, we use the proving ground to get information on usage of the equipment, and we use that data to feed test rigs in the laboratory where we can control, measure, monitor, and repeat very accurately, and we can compress data to make it playback faster so we can learn things faster. And we can use that information to feed our computer models and our analysis capability to increase the efficiency of our product development. What's the objective of your test? There's many things we can learn. Many things. You should start at the top of the page with what do you want to learn from this test? Not opening a catalog and say I want one of these and I want one of these. What information you're trying to gain and how are you going to get it? Obviously there's many tests that could be done, so we need to focus some. Typically we're talking about dynamic testing and durability. We're talking about fatigue. There's a lot of analysis capabilities for fatigue, a lot of FEA work. These log life contours can now be published. They look gorgeous, lots of colors, but it's very linear, very elastic. And we know when we're getting into fatigue and damage, we're getting non-linear responses. We're getting cyclic hardening and cyclic softening. We're getting into yielding. Material properties are changing as it's being cycled. What does that do? That says that the results of finite element analysis and other of these sophisticated computer models is still off by a factor of 10 from real life, from real tests. 10 times is too big a spread for us to build our products. We're going to have to do better, and that's where the test lab comes in. Again, we can source our information from the proving ground. We can develop our test capabilities, and then we can take that information and we can cascade it up to the development side, in the computer analysis side, and we can maximize the accuracy and complete Simulation capability. What are the steps in the test system concept definition? Well, what is to be learned from this test? There's that question again right up at the top. And how are we going to do that? We need to figure out our design parameters. We're going to need a certain number of loading actuators. We'll need transducers both to measure and control. So we've got to figure out which ones we need and where we're going to put them. What forces and displacements do we require? Is this kilonewtons or meganewtons, or where are we talking about? What are the stiffness and natural frequency requirements? If I'm doing a dynamic test and I'm exciting it across the frequency range, there's design criteria that I need to be careful of to make sure that I get good performance. What are the test control options? I'm going to need a displacement control or force control. That makes a difference in how I'm going to control the test, what transducers I need, and where they're going to be mounted. How are we going to adapt to different specimens? How are we going to simulate our boundary conditions? We need to get these things defined so we don't miss our key issues during the design stages. The next thing we have to worry about is data. Without good data, carefully analyzed and prepared, we're not going to get a good test. So we should think about how are we going to prepare our data? Are we going to look at frequency content? Are we going to peak valley slice? Is it going to be fatigue-based or loads-based editing? Time compressed, maybe to reduce some stroke or to compress time to make shorter tests. Are we going to take real-time data and we're just going to cut some pieces out? Can we do that? Can we paste it all back together and have it still work? We can do sine sweeps, block cycles. We can, today's computer world, we generate a lot of artificial profiles. We can combine those and figure out how we're going to use that data to control our test. I like to divide the testing world into two broad categories. Comparison and evaluation testing. Comparing A-B, for example, how many cycles does part A last and how many cycles does part B last? We test into a standard, a company standard, a government standard. We have to say a rollover protection machine's got to take so much energy in it, for example. Are we characterizing? Are we trying to measure the stiffness or the damping or the friction so that we can put this information into a computer? Those are kind of what I call comparison and evaluation tests. They don't tell you how many customer usage cycles that part will last. So then we move over to the simulation world. In the simulation world, we've got trying to test to real-world responses in real-world environments. We want customer and usage correlated durability type testing. If we do a good job here, typically these systems become more complicated, but they do a much better job of simulating the more comprehensive reality of today's modern world in a realistic way so we can learn from the failures. As you know, in engineering, we don't really learn much until something fails. Then we found out where the limits are, and the test lab is the place where we can do that safely. Comparison and evaluation tests, they show if a design is better, but they don't tell you if it's going to work better in the field. Doesn't reflect real customer correlated life. It's just repetitive cycles. Very few things in life see just repetitive cycles, the same cycles all the time. Can allow substantial test time compression. Generally simpler to run, just cyclic, usually 1 or 2 channel tests, for example. They don't include complex dynamic response. Many times we don't need complicated transducer systems and all that kind of measurement. But if we're getting into simulation, well, there we can reflect response to actual service. The failure results, the information we get, the measurements should represent real in-service function. We should be able to include complex specimen dynamic response. We're going to use real wave shapes with real frequency content and correlate the relationship between all of the various inputs to the response of our specimen. Generally, these tests are a little more expensive. They take more performance, typically more hydraulic oil or higher electric power. We need good quality transducers. But when it all is done, you've got getting much faster, much data in a much more accurate situation. If you're going to set up a test, what are some of the additional design criteria that you need? Not just picking actuators and transducers, you also need a test space, you need boundary conditions, you need reaction fixtures, you need bearings, you need all these transducers we talked about. How are they going to fit? How are they going to be mounted? How are they going to interface? How are you going to access a specimen? How are you going to adapt to different sizes in the future? These things really should be considered early in the test phase. Now we're going to cover a couple of specific examples where we go through the test definition, some of the design criteria, and we see how we can develop these around specific requirements for certain components. The first example we're going to take is a relatively simple component. It's a suspension link. It's got primarily tension compression loading, very common in a multi-link suspension. It's also common in many different types of equipment besides just suspensions. What is the loading environment? Well, there's rubber bushings in the end, and the things can get pushed and pulled on, and they can get twisted, and they can get bent. How critical are the twisting and turning and bending compared to tension compression? That would be the first question we might want to ask, and we can answer that question by doing some instrumentation and measuring some of the loads. We want to start with a free body diagram. As it says here, we're going to put tension compression loads on the strut. That's what we think is our primary damage. We're going to use a uniaxial loading, and we may consider torsional loading depending on the details, but we'll see. We'd like to avoid that. It adds complexity to the test, but we'll know more after we acquire some data. Now, what if we want to use the elastomer bushings in here? What do the bushings do for us? Well, if we were testing, for example, the welds at the ends where the bushings are attached to the strut, we might be very concerned about the stiffness of the bushings pressing on that wall and changing the strain in the weld. If we're interested more in these metal protuberances that are welded to the middle of the strut, then we're less concerned about the characteristics of the boundary conditions on their elastomers, and we could actually replace those with steel slugs or something else that would allow us to run much faster and not be limited by the real-time requirements of the rubber bushings. We don't want to overheat them. That'll cause a damage, that it's going to screw up the test, and so that would be a real problem. So we need to make that decision. What's the objective of the test? Again, what are we trying to do? What do we want to learn from this test? Do we want to learn the fatigue of the welds? Do we want to learn the fatigue of the stuff welded to it? Those are two different requirements, and really we could operate those as two different types of tests. How do we measure the local environment? Well, we can instrument the part, as you see here in the bottom. We've put tension compression, we can put bending, we can put torsion gauges on, whatever we're trying to measure, and then we can acquire real data, the real part, and real service. Another possibility might be to modify the part. We need to probably increase the strain. For example, in the picture on the right, we see that's a very beefy bar, very strong. And so we probably had a hard time measuring strain in it to get the loads. So as a result, we had to modify it. We had to weaken it. We had to increase the strain and put specific points in there that we could measure much more finer resolution to resolve the loads. Now we have to be careful when we modify parts that we know what we're doing. We're not changing the dynamic response of the part. We're not increasing the risk of safety problems. Those things all need to be considered. So if we're going to plan our suspension link component test, we can use this fairly simple decision tree to help us decide what complexity level are we going to need to run this test. First question, is this a multi-axial case? Well, we've said we're going to say this is tension compression, uniaxial loading only, so no, we're going to say this is not a multi-axial case. So good, all right. Then is the reproduction of frequency content important? Do I have to get the real data and the real wave shapes? Well, I would if I had the elastomer bushings included. Without the elastomer bushings, I'm testing primarily just steel or aluminum. They're not very sensitive to the loading rate or frequency. So then we could accelerate the test much faster and we get it done in much shorter time. Boom. We can learn the most amount in the shortest time if we can do it like that. If that focuses on the right area for us. If we're looking at the welds where the bushings are, well, then we're going to be forced to go real-time testing and we're going to take a lot longer to get the same information. In this case, we decided we're going to work on the welded part in the middle, not on the welds on the ends. That would mean we don't care about the specific waveforms or frequencies, and we can put in sinusoidal or block cycle type testing, which is easier to do. How do we set up a constant cyclic sine wave test and still get the right fatigue damage? Well, we've got to go through the rain flow matrix, fatigue damage contribution based on range and mean of each cycle, and we combine that with the material fatigue properties, the SN curve as it were, and by cycle we can accumulate the damage that's occurring, and then we can apply that to a specific strain level we're desiring to run in our test. You might say a maximum load, for example, and it'll tell us how many cycles will it take to have the equivalent fatigue damage in that new strain range. We can set up a couple of tests there, decide what's an acceptable length for the test, and then we can just run constant cycles. So in this case, we've taken and using fatigue-sensitive editing tools that are available in the controllers and in the software for the tests, we can take this variable time history data that we've seen here and we can reduce it to an equivalent representation that should include the same basic fatigue damage in the critical areas. Now, maybe we decide that because this is a variable amplitude time history with big cycles and small cycles and different mean levels, we want to simulate that more realistically. We can use what we call block cycle data to do that. Block cycle is basically sine waves with different mean levels and different amplitudes nested together in groups to more realistically simulate a variable amplitude environment. So again, we use our fatigue-sensitive tools to measure the sensitivity. We merge that with the fatigue properties of it, and we end up, in this case, we'll have mean loads and ranges in groups. So we can take the mean loads and ranges and we can develop this block cycle program that's representative of the same fatigue damage of that variable time history. And now we can adjust what the amplitudes are and how long we want to run it and things to maintain the same fatigue damage until we optimize our overall test results and test time. So what do we've got? A tension compression test for a suspension link. All right, well, basic requirements, 1 degree of freedom. We need to push and pull. We could do that, for example, with a load frame. We could do it with brackets on a T-slot plate. There's many options available based on what our capabilities are, what equipment we've got, how much space we have. We're going to do block cycle playback. And frequency is going to be limited by the bearings. If we include the bearings in the test, then we're going to have to limit the frequency and play real-time data. If we're going to eliminate those bushings, then we can put steel plugs in the end and we can run as fast as we would like to based on the capability of our equipment. How are we going to acquire sample data? We talked about instrumenting the part or inserting transducers into it. We need transducers both for control and for correlation. Control tells us how we're going to push on the part. Correlation says, is it responding realistically? Those are two different requirements and may need different transducers. Kinematic arrangements are going to be easy. Tension compression is fine. You know, that's a load frame job, or like I say, brackets on a T-slot plate. So based on this quick review, we can write our design functional requirements right from here. We need a bracket, we need this load, we need this stroke, we need this control capability. Boom, we can start designing. We can work right directly with the technician and come right to this test. Lower control arm is another example. This is a little more complicated of a test. In this case, we're looking at lateral and longitudinal loads. There may be other loads in the field, but in this case, we're going to simplify it to this. If you've got more specific cases you want to simulate in your test, then that would be expanded some. For this example, we'll talk about lateral and longitudinal. We decide we don't need to stroke it vertically. We're not testing the elastomer bushings in this part. We're testing the structure. So we're just going to fix it vertically. So we're going to run at 10 or 20 hertz or so. We think that's going to be enough to simulate the biggest fatigue damage on a part like this. And because we have a limited space on our base plate, we decided to use some levers and struts to compress the space and get it to fit within our facility capability, which is one of the things we've got to keep in mind when we design the test. So let's look at our simple decision tree again. Is this a multi-axial case? Well, in this case it is. We've got lateral and longitudinal coming in. All right. Is there a linear relationship between lateral and longitudinal? No, there's not. You can have a big lat load and a small longitudinal load or vice versa. That's workable. So that means what we're really talking about is we have to play multi-axial data into this specimen in a realistic amplitude manner in order to get real response. So is frequency content important? Well, if we're going to remove the elastomer bushings, again, we're talking about a metal part of some kind, it's not sensitive to frequency, then we can take and we can slice and dice this data down to compress it as much as physically possible. So in this case, we're going to say the bushings are tested separately, we're going to replace them, and we're going to test this as fast as we can. So what's our how are we going to do this? How are we going to put this together? We want to try and get this real-time data that's variable time history, as you see here, lateral and longitudinal, and we want to try and put it into something that we can time compress and play back in the laboratory. We got to have the right amplitude and the right phase, or we're not going to get the right results from our lateral and longitudinal inputs. They've got to be correlated, so we don't want to lose amplitude and phase information, but we don't really care much about frequency content. So that allows us the capability to do some compression. One of the tools we can use to compress data like this and maintain our multi-axial phase and amplitude is we can use a technique called peak-valley slicing. What that does is it takes a time history, it can be a multi-channel time history, and we sample all the time histories every time any cycle gets to a peak or a valley, a high or a low within the fatigue cycle counting. Then we take a dot, we slice through everything. We've got data now for amplitude and phase for all channels, and when we're all done, we've got all the amplitude and phase data, but we have lost the frequency content. The time has dropped out. Now we can play this data back however fast we want based on the capability of our equipment and our test requirements. For example, this is 40 seconds of braking events. We don't need to take 40 seconds to play that back. The fatigue damage occurs in a matter of a few seconds. So in this case, we can literally slide this stuff closer together, maintain the same overall amplitudes and fatigue damage, and play it back, in this case, 10 times faster or 8 times faster than real life. Now, in the case of a pothole strike or a curb strike, where we run into an event very fast, this whole event takes place in about a quarter of a second, requires several meters a second to keep up with. That's very difficult to do. So we're going to slow this event down. Instead of a quarter of a second, we're going to play it back in 2 seconds. And now our equipment capability is greatly reduced. We're going to get the same level of accuracy and fatigue damage with much less oil flow, much smaller valves, much easier to control rig. So that's basically your advantages of a peak valley test, is we can compress things very well. We can reproduce the proper loading because we've got amplitude and phase maintained from multi-axial inputs. We're able to slow down high performance events, and we're able to speed up slow speed events to minimize test time. Disadvantages, well, if there's frequency related effects such as testing elastomers or something, we can't do that because then we've got to have the right frequency content, we've got to have the right velocity. So we may not produce proper load in rate sensitive materials. Some composites and some adhesives now might be rate sensitive too. So as we're getting into these modern materials, we have to understand the sensitivity of our materials to the loading environment before we start to edit our data. So we can concept review here for our lower control arm. We said we're going to do a 2-degree of freedom test, lateral and longitudinal. We're basically going to do peak valley slicing for our playback, and the frequency is going to be limited if we include the bearings. If we don't include the rubber bushings in there, then we can play back at a much faster rate. How do we acquire sample data? Well, we've got to determine the test rig requirements. How much force do we need, for example? We've got to measure that. And then when we control it, how do we know what loads are representative of real service? We can do that by instrumenting the control arm, instrument the ball joint. There's many different options we can use to acquire that data. What's our kinematic arrangement? Well, we're going to bring in the lateral and longitudinal loads at the ball joint, as you see in the diagram there. We're going to fix the vertical with a strut so the arm doesn't swing out of the way, and then we can play these longitudinal and lateral loads into this, the representative amplitude and phase, and simulate the fatigue damage. Very realistic in the laboratory. So from this information, we can specify our requirements. We need this bracket, we need this actuator, we need this transducer. Boom, the functional requirements. So we've just gone through an example process for developing a concept definition for a dynamic test rig. We went through the set of requirements that we would do for 2 examples, a tension compression test and a multi-axial test for a lower control arm. The idea being that we're going to define what the test requirements are going to be so we know what our design objectives are, and we can move forward with the test in the most efficient manner and accomplish our goals satisfactorily. Of course, this is the first step in a long process for the full development of a testing capability, and we can talk about some of these parts in later conferences. Thank you very much for your attention.